So I guess we should start. The first thing to remind you on Friday is the deadline of the homework. So the second thing is about the plan of the day. So the plan of the day is we will finish this estimation topic, and we will start hypothesis testing. Okay. So there will be homework for estimation and sampling distribution. Okay. So we will release it probably next week after because other class is like one class behind, so it will be next week. And again, I probably will give 2 weeks as well, or at least 10 days to do your homework. So so don't worry about it. I mean, probably it will be a release on Monday, or yeah, probably or Friday. Yeah, that's fine. I mean, depends on time. So what we're going to do today is talk about finish the estimation, and then you have some time to talk about hypothesis testing. So for estimation, I want to remind you what we are doing these days. We have the idea is that we have just a dry graph. So what we are doing is the following, right? So the basic thing is like we have a population, right? Is the object that we want to study, right? In this in the population here, right? There are many people, right? Or subjects. I don't know why. Oh. Hello. Maybe I use this mic. Is that okay? I use this mic because this looks like I can't really use that. If you can't hear, then I go back to the original one. So there's a cross means an individual, right? Individual usually have some element we care, right? Say suppose it's income or spending, right? Or satisfaction, right? This is a data you want to look at, right? But the problem is we never able to look at every single individual. If you do, then we don't need to do statistics, right? Just collect all the data and do what we want, right? So in this, we're complicated a lot of object here. So usually we're interested in looking what we call some parameter, right? And some parameter may be the, say, if you focus on income, right, that will be, we care about the average income, right? In that sense, there's a mu, right? The average, right? Average is mu, right? Sometimes we also care about variance as well, right? Then this is sigma square. So these are two other parameters of the model, right? And we care, we want to know what are those, right? Of course, it'd be great if we know the distribution of this, right? We want to know, maybe we want to know how they looks like, right? The distribution, but that is too much to ask in general, right? So instead we focus on some of the summary statistics of this, right? Which is the first two things you come up with your mind will be mean and variance, right? Probably you want to also care about skewness, right? And also kurtosis, those kind of things that you might care, right? But in our class, we are not going to talk about this, right? Focus on mean and variance, right? And how to find this, right, is through estimation, which we cover in this class. How to do that is what we do some sample, right? We take this out, right? We will focus on a particular case where we look at the small pictures, And if this small picture is representative, which we call sample, right? Sample. Okay. This sample is a valid if this is a representative, right? Representative. Okay. This means that this small sample, we look at a small picture, actually would not deviate too much from a large picture, right? And how can we have a representative sample, right? That's what we learned last time, is what we call random sample, right? A random sample. And in particular, we focus on simple random sample, okay? That's the easiest case. That means that everything we have in the sample is actually what it should be in the population, right? So it actually, the sample, right? It would look like actually like this, right? Under the simple random sample, right? Would be look like, actually look like the same shape, right? And actually we learn, right? Particular last class is the sample mean, right? And a sample variance, okay? Are actually very good to estimate this, right? And why is the case, right? We learned last time, right? You want to do estimation, right? Estimation. Okay. And actually these are called estimator, right? Because that's how we do estimate. Okay. And we learned there are several good properties of estimators, right? We have unbiasedness, right? Is on average, what you want is what you get, right? Actually, what you have is like this, right? Expected X bar is just mu, right? And expected S square is also sigma square. So they're unbiasedness, right? They're also efficient and efficiency. And this is efficient and also consistency, right? Consistent. Maybe consistency, so because I use so that actually is a free good property, and we saw that X bar is a good thing, S square is also good, right? And these are called point estimation, right? Point estimation, right? Because you just use a single point, maybe that use a single point to do the job, right? Point estimation. Okay. And actually we have what we call, last time we covered, but we didn't go into more detail, it's called interval estimation. That will be the goal of today. And the idea is, instead of talking about a single guess, we come up with a bunch of guess, right? And basically what we want, maybe another slide that we are going to cover today, right, is the following, right? Because X bar under central limit theorem or normality assumption, this is true, right? The idea is this is the random variable, right? It can be here, can be anywhere in this one, right? So what we want is, we say, suppose the data give us this guy, okay? We want to extend left and extend right by M. And we want this interval, we have high probability that include mu, right? So the idea is this, right? Probability that mu is included in this, the left-hand side, right? This is X bar plus mu, right? And this is X bar minus mu, right? And we want this have a very high probability, okay? And we have 1 minus alpha. Alpha is being very small, right? Alpha is usually 0.01, 0.05, and 0.01, right? So this is a rather small alpha. So that is what we want, right? So that is called interval estimate, which we'll cover today again, talk about interval estimate. But this is what we have covered so far. Okay, I hope I give you a review that you would be happy. So before I proceed, is there any question? I would like to hear if you have any feedback. If any question. Okay, if no, Then let me go back to the slides and we go a little bit again, because I think that would be important, right? Estimation, okay. So it's a parameter, as we said, is reduced by theta, is something we care. It's usually summary statistics of the population, like average income, mean of income, right, or spending, right? And we have an estimator, which formally is a function of random sample, right? And random sample, you get a number there, and you would give me a number, right? Then usually this is depend on n, the sample size, so that's why it's theta hat n, right? The sample mean divided by n, sample variance by n minus 1, so they depend on n, right? An estimate is a particular realized value, right? So the distinction between the two will be important, as you will see, because we can talk about the probability related to the estimator, but we cannot talk about probability related to estimate, because estimate is the value you calculate. So I mean, when they realize, and then the estimate will be will not be we cannot say about probability, okay. Because it's not random variable. There are two ways to distinguish different type of estimator. One's point estimate, one's interval estimate, right? And some of you who know the news, right, probably understand we have a big market crash yesterday, right? It just like dropped like 1,000 points, right? And you would guess what happened today, right? I haven't checked it out, but in the morning I talked with my parents, and then they okay. What they asked me what I'm expecting, right? Then I give a number, right? It's like, I think it will be below the 15,000. That's what my point estimate, right? Then I would expect an interval estimate. I would say it would be 1,405,000, sorry, 1,400 to 1,500. Okay. That would be my guess, right? So that would be, if I guess an interval, then will be an interval estimator, right? If I guess a particular value, then it's a point estimator. So as we said, we have unbiasedness with efficiency, right? Unbiasedness actually means that in this graph is best illustrated by if three possible values, right? It's nowhere close to theta, but on average, it exactly in the theta. So that's unbiasedness, right? You need not have any relationship between your estimate and this individual one, but on average, it's hitting thing, right? So it's the idea that the idea of this is, although in reality you only do one sample, right, every time, but in case another one who replicate your study, right, or you do it another month, assuming the data doesn't change, the population change a lot, then you actually have multiple sample, right? At the end, you will figure out what's going on, right? That actually what happened in the real world, right? And the supermarket keep changing the price, right? To look at your demand curve, right? Today, this is the price, tomorrow, the other price, and another week, another price. And at that time, they trace down your demand curve and then try to maximize the profit. Also, that is what they believe, right? Because every week, the new price, and they come up with a new data set, and they can do whatever they want, right? Then that come up with, on average, hitting the target is very important. The second one, efficiency, right, is talking about comparing if the two estimators are unbiased, that is the average hitting the target, how accurate they are, and A is actually smaller than B because A is more inside than B, so that's A is more efficient. Okay. The third one is consistency. In this graph, it illustrates by the fact that, I mean, the subscript is 1 is sample size 1 is actually much outside, and clearly the way I draw this graph is it's not unbiased, so it's biased, right? Because look at the if you try to look at the 1, right, and actually this 3 in the middle is somewhere here, it is biased, right? You look at the second guy, the red one, the mean looks like here, right? And the green one, you look at this, looks like somewhat here, okay? And no matter what, you can see the trend is like it shrinks, and it should shrink increasingly closer to the theta. Eventually, you will be as close as what we want. Then that's called consistent. Okay, and of course, this is, as I said, is an advanced concept, right? Because it used the limiting argument, right? So, but I just want to have it because we needed to justify why we still use the variance, sample variance estimator for binary data, because it's consistent, okay? So the sample mean, as we said, actually satisfy all the three criteria. That's good. The sample variance of this n-1 satisfied unbiasedness, okay? And it's also consistent. And for binary data, the sample proportion is unbiased, okay? Because that actually also satisfy all the three nice property because of the sample mean. But the sample variance we have is not biased, okay? It's not unbiased. It's biased. It's not unbiased. It's biased one. But the fact is, we usually look at n is big enough, so it's a consistent. So it's not big issue. Okay, so that's why we still use this, although it's a bias. Because this is our estimate, so that's why when we look at the sample proportion, we use this guy. Okay, so now we have now we go to the interval estimator. Okay, so in this context, usually we need to assume normality, okay, assumption, because we cannot go anything further without knowing the distribution of sample mean. Okay, either you have normality, right, or you have large sample size, right? We call normality is assuming the underlying is a bell curve, okay, and you can never prove this, okay, because if you're able to collect all the data and prove it, then you're done, right? So then the question is how you can have an idea whether this is right or wrong. One way to do is look at your data, okay, your data, because you collect the observation x1 up to xn, right? It's your sample. And usually there are two ways, several ways to do it. One way is look at the skewness of this data. If skew is 0, then there's a first check, right? Because it should be symmetric, right? The second one, look at kurtosis. Okay. The kurtosis, is this around 3? If it is close to 3, then it's all good. Okay, that's a first way to do it. Okay, there's a first check, all right? And second check is you probably want to look at the data. You want to really plot a graph, right? Is it look like a bell shape? If yes, then yeah, right? Because if you assume simple random sample, right? This thing, right, actually should follow the bell curve as well, right? Because that is the idea of simple random sample, right? If the original bell curve, this is also bell curve. Okay, so that's the way to check whether they're bell, right? Or you can do a histogram, or you can do a box plot. So that is there are many more ways, but this is a way that you can check normality. Okay, we're not covering this class formally, but these are the way that you should consider if you want to be more careful. Okay, but usually we just being super lazy. Okay, just assume that's it. But usually, if you want to be more careful with your study, you should try to see if your data actually follow normal. Okay, because unless your data is very large, right? And then in that case, usually there is not a big issue, right? If you have, say, thousands or 100,000 data, looking at big data, then you don't need to worry about those. But if your data is not that big, then possibly you want to check. I mean, you can never know, because this is something we never see, right? But at least you can see from data you collect is a good one, right? So the question probably is, if your data doesn't show a normal, then what happens is collect more data, right? And you collect more data, then you should be more normal. But if you want to handle the case if in this not normal. There are many ways to do it, but it's beyond the scope of our class to handle those. But we will just assume that it's normal. And the other ways, as I said, is use a large sample size. Then we don't need to assume this, right? We can start from large sample size, n is big, right? Big N. Then we have this normal. Okay, so do remind yourself that when you do interval estimate, you need a normal. Okay, normal either come from your assumption directly, which you need to check, or you take big sample size. Big sample size you don't need to check, right? Is that okay? So now if you okay with this, then we talk about how to achieve the interval estimator, right? As we just hint in the beginning, right? So we just want this to happen. Okay, we want this to happen. We want, we know normal, right? So this random variable, remember sample means a random variable, right? We'll have the mean mu, okay? But we don't know where, okay? So what we want is we'll get some, we've got here, may got here, may got here, may got here, right? And in particular, if you get this guy, okay? And we want go left and right, okay? And actually for each one, we want to go left and right, right? And we actually want, if we do this, okay, we want to have a good probability, a high probability that actually that will include mu. Okay, that's the idea. Okay. And remember, normal is extend from negative infinity to positive infinity. So there's no way to make alpha become 0. Okay. The reason is if alpha becomes 0, m has to be infinite. Right? Because it extend way longer, right? It happened, your sample mean can be extremely large, then you need extremely big m. Right? So that is the m has to be very, very big, right? So that's why we have to make alpha, the value usually is like 0.9, 0.01 or 0.05 or 0.1. So these are the three value, right? That you would focus on. Okay. So, and later I will do the proof again to prove you this distance, the arm, okay, you extend left and right to make that probability very high to include the mu, will have this guy. Okay. This time I will present another proof that is easier. Okay, I try to easier is a little bit longer, but in this is I think it's easier to understand. We'll start from this to derive this answer. Okay, I change the proof. I still keep it old proof, but this is more direct proof. Okay, so let me do the proof quickly. Okay, so just to one more terminology, right? It's like it's an x bar, right? You go left and go right by m. Okay, and this is x bar plus m. This is x bar minus m, right? And they call this value is UCL, upper conversion limit, and this is called the LCL, right? And the m is called margin of error, okay? And the distance between UCL and LCL is called the width in W, okay? So that is the terminology, but I mean, just the name, it doesn't really have anything difficult. So now I think it's good to talk about this one. Okay. So how do we do the proof? So don't worry, the proof will be very simple. Okay. And the goal is trying to find m. So we'll be take a little bit longer detour. Okay. How do you do that? Okay. So how can we come from the first statement to this the second statement? Okay. Is so first look at the right hand side. Okay. So you can move minus m from both sides. Right. So look at this. Mu is equal to, maybe I put it here. Mu is less than x bar plus m. Okay. You can subtract m from both sides. So which is mu minus m is less than x bar. Okay. So that means that we go to here. So you can see the blue go to here. Okay. So that's how I move m to the other side. The other way ones look at this guy. X bar minus M less than mu, I plus M on both sides. So X bar is less than mu plus M. Okay, so that's why you go to this one. Is that clear how I change from the first to the second one? Is that clear? Okay. The next thing is from here, I would like to subtract mu from both sides, right? Then that should be easy, right? Look at this one. I subtract mu from both sides, so we add this one, right? Is that clear? Okay. And the same idea, I subtract mu from that side, I get this guy. Okay. I take away mu this. Is that clear? Okay. So then now I have other one that will also very clean is I divide every because this is positive, right? So I can divide this for everyone, this thing the same thing. Okay. So that's why I just go one step by step and I up to here. Is that clear? Is that clear what I'm doing? Okay. So actually the next step will be next page, but the main thing is this guy is by construction, this is Z, right? That's coming from the normality assumption we assume, okay? Because this guy is normal, right? This is coming from the normality assumption or central limit theorem, okay? Either way, you can do it either by normality assumption, you assume the underlying is a bell curve, or central limit theorem that will give you Z. This will be in the next slide, okay? This will be next slide, okay? Is there any question? If no, then go to the next slide, okay? Because central limit theorem normality will give this, okay? So now we can use our bell curve knowledge, okay? This is Z, okay? This is 0, okay? We want some symmetric length here. The is 1 minus alpha, okay? Symmetric means this side is alpha over 2 and this is alpha over 2, right? Because symmetric, right? Symmetric about 0, okay? And this is M over sigma over root N, okay? And this is negative M sigma over root N, okay? Inside is 1 minus alpha, right? Because symmetric about 0, okay? So if we call our notation, right? This, right? When you have the right hand tail is alpha of 2, right? This number is actually Z of alpha of 2, right? Or if you don't like this, actually this is just use the Excel, right? Will be just norm S inward, right? Alpha over 2, right? So that is alpha is like a very small number, right? So that is the way we handle this, right? And because this guy is actually this guy, right? So we can just move the denominator to the other side that give this formula. Is that clear how we arrive this? Is that okay? Why we arrive this guy? Okay. And if you don't, it's okay. Just the formula you remember is fine. I mean, that's how usually you learn the math. I mean, at the beginning, you may not realize what is the rationale, but you just take it. And if you do enough exercise, then you will see why this is true. Okay. So I hope this is you can follow, but if that is not, then take your time. So let me go over this example again. I think that would be important because that would be the thing that is the most useful one. Okay. So here we assume we know our sample population variance, which we will cover the case where it's unknown. Okay. You will know that actually we'll use T distribution. That would be something we will talk about later soon. But suppose we all know the sigma square, okay? And one of the things is how can we know this in reality? Usually you don't, but in some of the scenario, actually you do. Okay, like quality control, you know the variance, and sometimes actually there's some way to estimate sigma. Okay, and how you would do that is look at the historical data. You look at the range. Okay? You look at the data, right? That's a range, right? Range is the biggest minus smallest, right? Look at the range, and the range actually would tell you using some formula, which we will not cover in this class, and the range will have you can have a good guess on the variance, right? Because the range tell you to look at data what's the biggest and smallest, right? And that one actually can have some guidance of what it should be, right? Because the range is looking the smallest and biggest, right? Biggest and smallest, right? And the mean is in the middle, right? Okay, the distance, half of the range, right, will be a good estimate for the sigma, right? It gives you the upper bound, right, with the biggest sigma you can imagine, right? But you will be if you want to estimate better, then we'll be a little bit careful. But there's no harm to make it larger, right? You can overestimate, it's not an issue. The problem underestimate, okay? Because you get it bigger, the margin of error is getting bigger, right? So it's getting imprecise. That's okay. But you never have a problem have an imprecise one, right? So that is usually how you get the sigma. Okay, is look at the range, and you halve the range, right? Is the maximum variance, maximum SD you can get. Okay, so that is a one way to estimate the this guy without an issue, because look at all our data, you have all the data, right? The range, okay, and range half of your standard deviation cannot be more than half the range, right? Regardless of what the data, because the range is the biggest distance between the small and largest, and mean is somewhere in the middle, right? And your range cannot be too far away from that. So your SD. But anyway, some question, how come Z is 0.02? Oh, we'll cover that. Yeah, so don't worry. Yeah, soon. Okay. So now we are going to talk about this, but bear in mind what I said is this is we can have sometimes it's good estimate. Look at historical data. Okay. Because we can find upper bound always, because the standard deviation cannot be more than range. Okay. And there are some way to estimate those. Okay. But anyway, so we have a sample size of 64 and sample mean of 3. Okay. So the question is how to get a confidence interval estimate. Okay. And do note that first thing come from your head is X bar is already a point estimator. Okay, it's our point estimate. Okay, and that is the best we can get. Suppose we have to ask what is your guess, that will be 3. Okay, then we're done. Okay, the next question is, okay, can we do more? Okay, and we need to do, if you want to do more, okay, can tell more things, we need to assume certain thing, assume either normality, right? The reason is the central limit theorem might be okay, but you have to have a good hope of N64 is a good one, but yeah, maybe okay, but 64 may be okay, because usually we said more than 30 is fine, but it's fine. So how can we proceed from here? Now we remember the formula is like this, right? X bar plus minus Z over alpha 2 sigma over root n. Okay. And we have 95% confidence, right? That means 1 minus alpha is 0.95. Okay. So alpha is 0.05. Okay. So alpha for 2 is 0.025. So did I answer your question? I guess some question in the quant poll. Is it okay? No, maybe. I don't know. I don't know if it's okay, but maybe he just go to the washroom. But anyway, so that's why we have this one. How to get this? Again, it just come from the fact that just the norm S dot inward. Oh, sorry, I have to use 1 minus alpha/2. Okay. Because of the inverse, look at the left hand side. Okay, because this is 0.025, right? And this is 0.975. Okay, so that's how. Let me look at the Excel. It should give you the 1.96. So I open Excel. Okay. Oh, again. Let's see if I can solve this problem. Okay, it's not working. Okay, that's okay. Well, I don't know what happened. So it would be norm dot S dot Y inward, because you are given probability, you want to find the Z. Okay. So it's 0.975. This is the entry as we have written down here. Okay. So that's there's 1.95996. Okay. So some of you has asked me how many common places you need to keep for your assignment or your test or whatever assessment. I think you just keep 3 to 4, maybe 5. I mean, I don't think we're that picky. Okay. If you just have 1 decimum or 2 decimum off, as long as everything looks all right, I think it's fine. Okay. But now I hope it's clear how we have this. We get this number 1.96. Okay. And for the rest, we just plug in the number, right? Because this is 1.96, and this has come from the assumption of 4, and this n is coming from 64 here. Okay, so that's why you plug in the number there. That means that you have to, whenever the mean you have, you go left and right by 0.98. Okay, and do note that this ME is independent. Okay. This M is independent of X bar. Okay, it's not with X bar. It's you calculate before you do the sample. Okay, there's nothing with the sample. Okay, except the sample size. If you decide the sample size, it's already M is fixed. Okay, so you go whenever X bar is, you always go left and right by the same margin. Okay, so what at the end you get is you get the point estimate. You add left and right by 1. So that means that you would have an interval estimator is 2.02 to 3.98. Okay? So it's between roughly it's between 2 and 3, 2 and 4, right? So the estimate you would say it's 3 and the best. But if you ask me to give an interval, I would say with 95% confidence that will be between 2 and 4. Okay. Do note that here there's some terminology we have to emphasize, we discuss now, is why we call confidence. Why we don't say probability. Okay, why we just suddenly change the term. Okay. The reason is being that once you figure out the interval, come the number, you cannot call probability. Okay, because it's either the interval contained it or it didn't. Right? You just don't know whether it contain or not, but there's no uncertainty here. Okay. Once, let me repeat the statement. If you get a number, either it's in or it's out, there's no probability. Okay. In classical sense. Okay. There's no random experiment to be conducted here to assign probability. Okay. And so that's why we say confidence. So by confidence, what do you mean by that? Okay. By confidence means that suppose we do this procedure, say 100 times, okay, and it will be 95 out of 100 of them will include the true mean mu, and 5%, 5 of them, so 5%, 5 of them will not, okay? But we only do just once. So that means that we only have 95% of confidence that will be there, okay? There's no probability. We can't say probability. We can only say probability before we do the random sample. Before we do the random sample, there will be 95% probability that will be included. But once we do it, it will only be about, we only can say about confidence. Okay, is that clear what it is? Okay, it's not, that's why it's confidence. We don't say probability interval. That's why confidence. Okay, we just have to say confidence. Okay, that's it. Is there any question before I proceed? That's clear why confidence is because of, again, it's because of once we found it, there's no more probability there. Okay, so that's why you only can say confidence. Okay, it's not okay to say the 95% that the sample mean will inside. You can't say it. Okay, in the terminology we use in probability, right? The probability we assign is we have some random experiment. Before we do it, we don't know which one, and that's probability we can assign, right? But say suppose I toss a coin. Once I toss a coin, right? So before I toss a coin, right, it is going to be head or tail, right? But once I toss a coin, I close it, you can't see it, right? Then there's no more probability. You just don't know it. Okay, there's no probability. It's one half is tail, one half is head. It's already either head or tail, right? There's no probability there. Same as common interval. Before we do it, we can say probability. Once we do it, we can't. Is that clear? Just the terminology. Okay, any question? I mean, it's not very important for when you apply it, but you have to know terminology why it's confidence. It's because of we can't say probability. Okay, that is what is here. Okay, so it's what it means is actually this, right? Is, as I said, right? If you do this, you have 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 this, and 95% of this you construct will include the mu. Okay, and says 5%, right, will not be included. But do note that we don't know which one will be included, which one is not. Okay, so that means if we just do one, we don't really know. Just confidence. Where some confidence is there. Okay. So we go to break, but before we go to break, I just want to hint you that after the break we talk about this is, suppose we don't know sigma. Okay, that is actually usually we don't know. Then we will use S squared instead. And in that case, okay, we know by normality. Now we cannot use central limit theorem. You have to use normality. When it's normality, use the same procedure here, because before I just said alpha 2, and this is sigma. Okay, you just replace S and replace by T, then everything will be the same. Okay, so that means that we will have, this is the result. Okay, so basically this is what we're going to talk about. After the break, we'll go through the example, and okay, so let's have a break. I go around to see if you have any question. Let's resume at 1:30. Okay, let's return. So so I guess we continue what we talk. Okay, just to remind you one thing, right? If we know the sample variance, okay, so population variance, then the interval estimator is plus minus set R over 2 sigma over n, which we have covered. And some of you told me during the break is we have so many formulas. Yes, unfortunately, we have many formulas to remember, but not remember to understand. You need only remember, because when you do things, you always have the formula in your slides, right? In your notes. So this is not a big deal, right? And some of you, yeah, that's okay. So as if we don't know, we use S square. So how can we do it? It's the same, right? We just talked about before the class, the same thing. Okay, it will be T n minus 1 alpha over 2 S over root n. Okay, so the only difference is when we replace sigma, we replace by S, and we also have this Z replaced by this guy. Okay, so the idea is the same, right? Because now we have a T, right? So everything just same idea, same proof will follow. I'm not going to repeat it because the same thing. Okay, you the same proof, right? The same idea, right? You just ask the question of, right? The question is asking to construct this, right? The same idea is asking what's probability that mu is between x bar plus m and mu x bar minus m. You do the same operation, everything is done, right? Except you apply this the very last step, right? The same thing. Okay, I hope you can see the same proof behind. Okay, but of course, I mean, if you don't feel comfortable, then you can just forget about the proof. Remember this particular one, and then although we don't write that down, this is the margin of error, right? This margin of error. Okay, and the width will be 2 times the margin of error, right? And then you have UCL and LCL, right? I don't think I need to write that down, right? Because I think that is something is obvious, right? So I guess it's good to go to example and see how you apply this, right? So this is the question. We assume normality, right? So it means that we assume the underlying thing is a bell curve, okay? Remember I said is you can never prove it, okay? You can just look at data and see this is valid or not, okay? This is something we can't really, we can not prove, we can verify whether it's valid or not, but this assumption we're going to make, okay? And we consider a random sample of N20, okay? And so N is small, so that's why probably the central limit theorem doesn't really apply, right? N is small. And sample size is 3, and S is 12, okay? So before we start, notice that X equal to 3, this is a good point estimate, okay? So this is the thing that we should bear in mind. Before we do anything, people ask, what is our guess on the mu? Okay, that would be 3. Okay, mu will be we'll just say 3. Okay, so now what we're trying to do is, okay, can we get a better estimate? Okay, or more details on the 3, right? So because 3 is just a point, right? We want to see what are the possible outcome that you can get from that. Okay, first thing is what I want to do is the same idea. Okay, we want to find T n minus 1 alpha over 2. Okay, the idea is again is the same thing, is we want this T, okay, 0 is here. You want this area is 1 over alpha. Okay, that means that this guy is alpha over 2, and this is alpha over 2. Okay, and how can we know this guy? Okay, how can we do this, right? This will be T dot inverse. Okay, and you put this is 95%, right? This in the middle is 95.95. Okay, and both sides will be 0.025, right? Because the middle is 95%, both two sides is 5%. Half of one of this must be 25, right? So if you look at this, that means that, okay, the right hand side is 0.025. Okay, that means that the left hand side is 0.975. So that's why 0.975. And N is 20, so it's 19. Okay. So that's how 19 is here. Here, that's how what Excel would give you. Okay. And I will show you how to do it in table. But before we do it, I show you the Excel first. Okay. That is this number, right? T19 0.975. So that we do it here. Okay. T dot inverse. Okay. 0.975. Okay. 0.975. Degree of freedom is 19. Okay. So that we have a 2.09. Okay. So that is what is here. Okay. And I mentioned T table. I want to show you the T table as well, because I think I never told you T table. Okay. You go to the Excel here, and there are many T tables. I just pick up the one, say this one. I just pick this guy up. I took the dummy website. Okay. So here you have this table. Maybe it's a little bit too. Maybe I finish the question and come back to this one, because I think I need to erase the thing. Otherwise, it will be. I'll talk about this after I finish this one. Otherwise, I have to erase off everything here. Okay. So that's how I put it, the number in here. Okay. I put 2.93, and I put S is 12 is here, right? 12 is here. Okay. And N is 20 at the here. Okay. So the margin is very big, actually 5. Okay. 5.6. So that means that your estimate, your point estimate is 3. Okay. And have to go left and right by 5.6, right? So it's either this number or this number. I think I made mistake. Should not be this one. Because 3 minus. Okay, I'm sorry. There's typo here. So it should be 3 minus 5. Right? 5.616. Oh, man, that's all right. Sorry, there's no problem with the slide. So that's correct. So that's correct. Okay, so that is what we have. Okay, negative 5.96, and this is the right answer here. Okay, so is it okay that I erase this slide? Okay, so let me erase this one. Okay, and I would like to show you how to find this from the table. Okay, I mean, of course, when you do your assignment, you can basically go to the Excel, right? But there are times that you need to refer to the this one. So let's see. So let's open the image. Okay, that I think that's good. Okay, so how can we do that? Okay, this one is very good because this one actually gives you the right hand side. Okay, right tail. So what you need to do is look at, there's the table actually have column and row represent degree of freedom. Okay, the column represent the tail size. Okay, and the tail size we need is 0.025, right? Because alpha is 95, right? So 1 minus alpha end up is this column. So we need this column. Okay, the column number 4. So column number 5, the 5th column. Okay, and then we look at, remember we have 5th column, and then we just go down to check out which is the number. The 5th column, the degree of freedom is 19. Okay, so this is number 2.93. This guy. Okay, the 5th column. Look at the 19. So we see. Is that clear how we get this number? Okay, and likely you will print this out and bring to the test venue. Okay. I know I do, and some of you reflecting that checking table is very old-fashioned. But given our exam technology, we can allow you to bring the Excel. I mean, but that's the fate. But that's current state of the world. But I can't do too much about it. But I'm pretty sure 10 years from now, probably we will be everyone will bring their laptop to the exam. But for the moment, I mean, we have to accept some obsolete technology being used for the exam purpose. Okay, is that clear? I mean, now if you collect data, you got a sample mean and sample standard deviation, then you can have a good guess of what the population mean should be, and you can give a 95% confidence. Okay, so that is very good, because that is how you can use the data, right? You collect data, you do this operation, and that's how you guess, right? Of course, this interval, if they're getting smaller and smaller and smaller, then the better, right? And when you have a large sample size and it's getting bigger, this automatically will get smaller, right? So that means that this one looks maybe look terrible, right? But if your n get bigger, and likely your s also would get small as well, okay? And the t will also get smaller as well. So basically increase n, usually reduce this guy, right? Increase this guy and reduce this guy. So unambiguously, everything will get smaller, right? Because when n increase, s tend to drop, right? And this t n minus 1 alpha also drop. So this guy drop, this guy drop, and this guy up. So everything is going to go down, and then the margin of error should go down, right? So if you increase the sample size and everything would be nice. Okay. So if you don't like this one, then you have to increase sample size. Okay. And later we'll talk about what should be the appropriate sample size, right? Because you want to guess this one, and what should be the n? The question is, right? Because we decide how much sample to collect, right? And same as when you do the project, maybe some of you do survey, right? In that case, you need to decide how big the n should be. Okay, this actually gives you some idea. If you have, okay, but we'll talk about that soon. Okay. And now we actually go to another formula, which is not surprising, okay? Because this is the sample mean x bar, right? And root p1 minus p, right, is an estimate of the sigma, okay? Okay, and that's done, okay? So do look that here is we can still use that. Okay, we don't need to use Tn minus 1 alpha over 2. Okay, the reason is because this is a binary data. Okay, we are using normal approximation, right? So this is if you remember the formula when we have p, okay, with a normal with pi 1 minus pi and n, right? And then we basically replace this by p, right? We could put our sample 1, right? But that would be biased one, but that's okay. This is consistent, so that's why we use this formula, and we still keep the n. Okay, is that clear? So let me see example will be more useful, because this is a rather a useful technique. Okay, is the following. Okay, so you are asking the question like, okay, a random sample, okay, of N64, right? So what you're asking indeed is you are talking about whether, okay, people like cats or not, right? Binary 0 or 1. Okay, and you've got a proportion of 0.3. Okay, so then you get 30% of people like this, okay? So the question would be, how do we proceed, right? So it just, the formula is just P plus minus Z alpha over 2, okay? P1 minus P over N. So just basically plug in the number, okay? So what you're going to do is just plug P is 0.3, okay? And everything just, this Z is 1.96, we know it, right? So everything is just plug in, you get 0.122, okay? So what you will say, you guess is 30% of people like cats, okay? And then you plus minus, okay? So end up in this one, okay? So that is what we have. Is that clear? So just plug in the formula. So there's nothing deep here, right? Just saying the logic is also actually the same. Is that clear? Is that okay? Any question? If no, then we probably go to the very last part, right? Sample size, okay? Sample size is the idea that we go a little one step earlier, okay? We have to think about how much sample you want to get, right? Because to sampling, with the first thing is to decide how much sample to get, right? So, but we know the last step, right? We want to make sure that our accuracy, right? We want how big the accuracy we want, right? So the idea is we want to go back, okay? We decide what would be our margin of error and we ask N. So basically just reverse. So basically what we've done is we have, the question is like, we have, no, this is the formula, say this is the, okay? And we have N sample, okay? And we end up with this guy, right? And do note that, remember this guy, the margin of error is independent of what you do, right? Independent of X1, the sample, right? It doesn't really matter what sample you got, what the value you got, right? What the value doesn't really matter, okay? So this is called ME, right? So once you do the sample, you can calculate this, okay? So now the question is go backward, okay? Suppose we want to make this M is our accuracy, right? The margin error. We give you the accuracy here. We go to ME. We want to back down what's N. How many samples I want to get? Okay. At the ME, okay. And I give you alpha as well, right? I give you sigma. I want to find N, right? Because that is easy, right? Because ME is indeed this guy, right? That's the definition. Okay. The question is, now I give you this guy. I give you, this is what I want to achieve. I give you alpha, that you can calculate this guy, you're done. I also give you sigma, this is done. So I want to find N, okay? This is just solving equation, and that's what you learn in your primary school, right? There's a primary school math here, right? So you can easily see N will be just sigma over 2, C of sigma alpha over 2, sigma over ME here, okay? The square root of N, right? And then you can square both sides, and it's just Z alpha over 2, sigma over ME square. So just square both sides. So that is this formula. Actually, you will see from the next slide. Okay, it's here. Okay, that's how you can prove it. Okay, so what I do is, if you assume normality, central limit theorem, if I know sigma, this is the what we want, right? We have, I tell you this, I tell you this, I tell you this, you tell me that. Is that clear? And this is the formula. Okay. And probably you ask why I have this run up thing there. The reason is if this guy turn out to be 14.9, okay? So what you want is you want to have a 15, right? If you have 15.1, then you want 16, right? Because it's okay to collect one more, right? Because you want to make sure the margin of error is at least, at most, the number I give you. So that's why the sample size that you need is you get a one more than that. Okay. Of course, if you get exactly 15.0, then of course you get 15, right? But you just make sure that it's run up. Okay. Is that clear what we're doing? Okay. The goal is we give you how large the margin of error, you tell me what's n. Okay. That's actually what happened when you decide to do a survey or you do a questionnaire. You really want to know how many you need to get, right? But this is a very practical question, right? Is that clear? So let's see the example. So the same formula here, there's nothing new formula, but just the formula I write in this way, just like easier, right? Because basically you just solve the equation, right? So let's see this example. Okay. We have a population. The for normal is important. If you don't have that, everything cannot be done. Okay. I have a sigma is equal to 10. Okay. And as I said, sigma can be guessed from data. Okay. But we just don't tell you how to get it, but that's a certain way to guess. Okay. And I have 95% confidence. Okay. So remember, alpha will be 0.05. Okay. Because that's 1 minus alpha is 0.95. Is that clear for this one? Okay. Now we have the population mean is within 4%, within 4. So that means the margin of error is 4. Okay. So the question is, I want to estimate something. Okay. I know the population standard deviation is sigma is 10. Okay. I want to construct later. I want to estimate the sample mean, and after that, I want to do a 95% confidence interval, and I want the interval cannot be more than 4. Okay, so that's the goal. Then I need to ask ourselves how many samples we're going to get, right? So that's the idea. Is that clear what we're doing? Is that okay? Okay. And first thing, we need to know the formula, right? And it's just, if you check the last slide, it's this, right? That is square times sigma over ME. Okay. And we have been doing this a lot of time. Set 0.025 is 1.96. Okay, this is something we have been worked so many times, but I just write down again the Excel formula will be T dot inward. Sorry, not T. Sorry, it's a norm S dot inward. Okay, you look at the right hand side is 0.025, right? Because you want 0.95 is here, right? So this is 0.025. This is 0.025. So the left hand side is 0.975. Okay, 0.975. This will give 1.96. Margin of error is given to you. Is here. Margin of error. Okay, and basically what you do is you plug in all the number here. Okay. And this can come from Excel or whatever you like. You get 27.01. Okay, and you have to run up, so that's why 25. You just need 25 samples, and then collect data, and no matter what the result is, then your margin of error will be less than 4. Okay, is that clear? So this sample size, you calculate the margin of error is dependent, right? But it just tell you no matter what you do, right? Just like what you see here, X bar is here, the mu is here, okay? No matter what you found, okay? What is it? You will go left by and right, okay? By 4, okay? This would be fine, right? Would be 4 as long as you have n at least 25, right? Then this will satisfy, regardless of actually the sample is, okay? You would go left and right by 4. Is that clear? Okay. So I think the next one would be more useful. And actually this one can be closely related to what you observe in the real world more often. Is you look at the binary data, okay? Binary data the same, right? But just this guy, right? Is this, we look at these, we know this guy, right? This will be the sigma, right? The sigma is this guy, right? Sigma square, this sigma square, right? So that's why sigma is just square root of this guy, right? So I hope this is clear, you know the same thing, okay? So that's why you just replace the formula same, right? But this guy is just sigma square, okay? So everything is same, right? But just the same thing. Is that clear? Because remember the formula is like this, right? Is that over 2 sigma square, this guy, right? ME square, right? Do note that there's no difference, right? Because this binary data is same as normal. Just because binary, we can just have this pi. Is that clear? Is that okay? So later you will see why this is very soon you will see why this is a very useful one. Okay. So suppose, okay, we know pi is 0.04. Okay. And you may ask how we can know this. Okay. Later after this slide, I tell you, you don't need to know this one. Okay. We don't have to know this guy, but suppose we know pi is 0.04. Okay. We just do an example. We know pi, but later we will show you we don't need to know this one. Okay. So suppose we know this one from historical evidence. Okay. And you want to have a good estimate. Okay. Maybe sometime you know this guy. For example, look at the COVID cases, right? And you probably know how many people would got COVID every day because it used to be fairly stable over time, right? So if you want to check this out, then this is a fairly stable thing, right? So we want this set 1 over alpha is 0.95. Okay. So that means alpha over 2 is 0.025. Okay. And we want the margin of error, right? The ME is 0.01. So that's the question is being given to you. Okay. So the question, of course, asking what the sample size, right? The first thing to calculate is calculate the population variance, right? Because the will be pi times 1 minus pi, that is 0.024. Okay. And okay. And this is 1.96. I think we have done so many times. I'm not going to repeat it. This alpha is 0.01. Okay. So what's left is just you plug in every number there. Okay. Do remember there's no square for this one because it's already the variance. So what you get is 92.19. So that's why you have 93 samples needed, right? So in this case, you need 93 samples to do what we want to do. Okay. So I guess that's not an issue. Okay. The issue probably is how can we know this guy? Okay. And the question is very simple, turn out to be. If you don't know, actually that's the most of the time, is we will use actually 1/2. Okay. Why is the case? Because 1/2 will maximize this guy. If you remember the graph we have, right? If you try to draw pi 1 minus pi, draw this graph, okay? Pi is here, pi must be from 0 to 1, right? Because proportion, right? The graph will be like this, right? So this is 1/2. It's on your slide anyway later. So this is the maximizing the variance, right? So if you don't know what to do, I choose the most conservative choice. The worst case scenario is 1/2, right? And in that case, I would always have enough sample, right? Of course, at the end, the margin of error at the end when you calculate is probably smaller, right? But that is the best. That's the easiest one we can say. Okay, so let's see. Okay, so because this is the idea is because this is the highest, so we choose the most conservative one. Okay, so here is the thing that we are using is if we don't know anything about pi, so what we're going to do is we have a 95% confidence. We have the proportion. I wanted the margin of error is between this guy. Okay. So what's changing from here from the last question is just only the first one, pi is 0.5, and that's why we have this guy, right? We use this 0.025, so this only changes. Okay. And turn out that this guy is 97. Okay. So you easily see that when you see in the daily thing, you talk about how many people like particular guy to be in the election, right? They would ask, you can see, right? They would need to ask 100 people to achieve ±1, right? And if you want to be more accurate, okay, do I have this slide? Oh, I don't. But if you want it to be, say, 5% or 2%, actually, you can easily see that if you would usually, if you want to be plus minus, say, 5% or 2%, you need more like 1,000 or 2,000 sample, right? So that's why you can see in the US election, right? A lot of poll actually doing by 1,000 to 2,000. Okay, that is actually the reason behind this, because say whether you support, say, Joe Biden or Donald Trump, right? Or recently the election on UK, right? But anyway, but these are the things that you would understand why they would just collect several hundred or even to 1,000 was sufficient, right? Even though you can see, even though say US has very big population, when you see the poll, okay, in the US and the UK, they don't make much difference. They always ask 1,000 or 2,000 people, right? Even though US is much bigger than UK. The reason is like this, okay? Is that clear? It doesn't, I mean, when you do things in Hong Kong, they also do similar sample size. It doesn't have to, the size of population is not really matter here, right? It's just like independent of that. No matter how big is the population, the sample you need is the same, right? You want to have the accuracy, that's what you want, independent of how big actually it should be. Is that clear? Is that okay? Okay. So very, very lastly, I want to mention two functions which related to what we covered this class, but they are not important because you know how to do it. Okay. I think it's not very important because they just combine the calculation we know. Okay. So basically, if you want to calculate the margin of error, actually they call confidence norm, actually the margin of error. You just tell them the alpha, remember not alpha 2, but alpha. You give them the sigma, give them n, that give you directly answer. Okay. And same for the confidence T, you give them alpha, give them the S, give them an N, then they give you the answer. Okay. But right, but this is nothing but just do the calculation directly. Is that clear? What is it doing? I mean, I guess it's not very useful, okay? Because you know how to calculate each of those. Besides, it make it more elegant in your code. Okay. Is that clear? Is that okay? Any question? Any question? If no, then we're done with this topic. Okay. So I want to, the last 5 minutes, I want to give you a very brief view of what we're doing in the next class. Okay, you will be more relaxing because I know some of you will go into a midterm today, so I try to be very relaxed. Okay. Here is this. We do hypothesis testing. Actually, that is actually very similar to what we have done. Why? Now remember what we are trying to do. What we have just done. Okay, what we just done is the following, right? We have a data. Okay, we have the population. Okay, there's a bunch of data here. Okay, we want to know a parameter mu here. We want to know this guy. Okay, and how to guess this guy, right? Is we take out some sample here. Okay, some sample. Okay, there's some sample here. Okay, and we come up with the mu. Okay, so come with X bar. X bar is our guess of the mu. Right, that is the point estimate. Okay, and we also have the other thing is we can also have this guy plus minus. Okay, that will be our interval estimate. Okay, so and how it related to hypothesis testing. Okay, the idea is very simple. Okay, we just almost reverse what we are doing. Okay, so we use this to guess this guy, right? That's what we just said, right? Guess this guy. Okay, and the question now is, if we know this guy, suppose, okay, if this is within this range, then we would tend to say this is supported by your data. Right? Let me repeat the statement. Okay. Suppose we are going to claim this one is, say, 100. Say, okay, this is our claim. Okay. And we collect data, the data lot, the data is 19, so 90. Okay. And confidence interval set, okay, is this M is like 15. Okay. So this guy, you would put it like 75 to 105, right? So that is what is your guess, right? Suppose this is the case. Okay. In that case, we see that our data actually is kind of supporting this claim. It's not contradicting this claim, right? Because 100 is still within the range that we try to guess, right? So this is supported, right? But in the other scenario, suppose someone claim it's not 100, his original claim is like 110, okay? Then you would say this claim or hypothesis is getting rejected. Okay? It's because this is far away from what we guess. Okay, so that's why hypothesis testing is essentially kind of reverse way of we do estimation, right? Because we estimate, we don't know what it is, right? This is our guess. But hypothesis testing is if what we think it should be is not within what we guess, then we think our original hypothesis are sometimes wrong. Okay, so because suppose we think it's 100 is within what we guess, okay, we're fine. Okay, but it's far away from that, no. Okay, so that will be the goal of the next three classes. Okay, so I will see you on Thursday. Thank you. Have a nice day. For those who have midterm, good luck. So stay a little bit for answer the question if you have any.